Okay, so back to this diagram. I think we explained it very well last time, but let's go through it very quickly again. So the most important point here is that everything goes through the ready queue. When a process is ready to take the CPU, it's in the ready queue. And if a process gets the CPU, if it's in the ready queue and the scheduler decides to give the CPU to that process. If the scheduler decides to give the CPU to that process will become running. Remember, running, in this course, in operating systems, running means on the CPU. And ready means waiting for the CPU. So ready means waiting for, although it's actually waiting, but we don't call it waiting. The technical term for a process that is waiting for the CPU is not waiting, it's ready. Waiting means waiting for something else, like an I/O device or an event, as we will see. So now when a process requests I/O or needs to wait for an event, the system is going to put it in the waiting state. And the process will be in the waiting state until that event occurs or until I/O completes. Whenever that happens, the event completes or I/O or event completes, the process will be placed in the ready state. So a process never gets the CPU directly. Now, this is the main point here. A process never gets the CPU directly. It has to go to the ready queue because other processes may be interested in the CPU as well. And who resolves this conflict? Who decides which process gets the CPU or which process gets each CPU if we have multiple CPUs? It's the scheduler. Okay? Now what will happen if a process performs an invalid operation? So a process is running. Of course, if it performs an invalid operation, we know that it's running. Then, if a process performs an invalid operation, what kind of transition will take place? To which state will it transition? The transition will be to termination. So transition from running to termination could be for a good reason, which is normal termination, a process just completed, or it could be for a bad reason. If the process performs an invalid operation, then the system will terminate it, will kill it. Yeah.
So on the very first process that needs the CPU, when the system is started, it doesn't go through the ready queue?
It does go through the ready queue. So that's how the system is designed.
Okay.
Yeah. So everything has to go through the ready queue. Well, even when the system starts, it may launch a bunch of processes. System processes, so it's not going to launch one process. Normally, if you look at your task manager on Windows, for example, you see a bunch of processes that were launched by the system itself. So normally you will have multiple processes, and the ones that are ready will be in the ready queue. Okay, now we will look into an important concept, which is the process control block. So this is a data structure in which the system will track all the information that it needs to track for each process. So in the process control block, you have the process state, what's the current state of a process, the program counter, which is the address of the next instruction for this process to execute, values of the CPU registers. We'll talk more about this in a little bit. After we go through all of them, we'll discuss this in further detail. Scheduling information, like the priority of a process, and the information that the scheduler needs to track for a process. Memory management information. We will fully understand this when we get to memory management. Accounting information, like how much time the process has spent on the CPU and how much time the process has spent in total like the process has been running for 10 milliseconds, or 10 seconds, but during these 10 seconds, the process wasn't on the CPU all the time. It was on the CPU only for part of these 10 milliseconds. So the system tracks all of this, and unfortunately at this point it's not clear why the system needs to track this. Tracking this is important for scheduling because scheduling decisions are based on the process's past behavior. So the behavior of the process can be characterized by keeping track of how much CPU time, how frequently the process requests I/O, and all of these process behavior things. I/O status information, the I/O devices that the process is currently using, list of open files, etc. So, the operating system is a program and it has its own data structures, and one important data structure is the process control block that tracks the behavior of each process and the state of each process. Now the interesting question is, why does the operating system need to store the values of the CPU registers in the process control block?
It knows which ones it can use at any given time.
Which ones, when you say ones, what do you mean by one?
So which it knows which registers are available.
No, when a process gets the CPU, all registers are available to that process. So if process number 1 is on the CPU, so this is the CPU, and the CPU has a bunch of registers like register A, register B, register C, etc. A process has the CPU, so it has access to all the CPU registers. So it may put the value 17 in this register and value 2 in this register and value 9 in this register. Now, why does the system need to store the values? Yeah.
Because when the process gets taken away from the CPU, it might need to go back to what it was doing in the CPU before, so it needs to reload those values back into the register.
Yeah, exactly. That's exactly why the system needs to store the values of the CPU registers for each process in the process control block that belongs to that process. Now, the process control block is an object. Each process has an object, an instance of that class, which is the process control block, in which the system must store all of these values so that when process number 1 gets interrupted, and it will, in a typical system, it will get interrupted by the typed interrupt or because it requests I/O. So when it loses possession of the CPU, the system needs to store these values so that when process 1 gets the CPU again in the future, it will pick up from where it left off. Okay? So this is a very important piece of information that the system needs to store in the process control block. Okay. Now this slide just gives us a feel of what a real operating system looks like, or reminds us that an operating system is a program. It's a program that is written in C here. This is Linux code, and this is what the process control block looks like on Linux. It's a struct. It's using a C struct that is called task struct. It has the process ID. It has the state. It has the time slice or the time quantum, pointer to the parent. Each process has a unique parent. List of children. A process can have multiple children. List of open files. And a pointer to another data structure that tracks memory management. So memory management is a complicated one of the complicated modules in an operating system. And for memory management purposes, memory management has its own data structures. And in the main data structure for a process, we have a pointer to that data structure that tracks memory management information. Okay? Now, this is an interesting diagram that illustrates transitions, that take place in an operating system. So, in this case, we have process number 0 executing on the CPU. So process number 0 is on the CPU. Then it gets interrupted for one of many possible reasons. One reason is the timed interrupt. Another reason is making a system call. For whatever reason, if a process loses possession of the CPU, the system, the kernel gets the CPU. And the very first thing that the kernel does is saving the state of process number 0, saving the values of the registers and the program counter, saving the program counter, which points to the next instruction to be executed in that process. So that when this process gets the CPU again, the system knows from which instruction it should start or restart executing that process, or which instruction should be executed next. Okay? And remember that when the kernel gets the CPU, the kernel itself is a program. And the kernel, when the kernel does its job, the kernel is a program. So it will be doing some work and it will need the CPU. So when the kernel gets the CPU, it will be modifying these registers. It will be changing this to 5 and this to 12, possibly. So that's why we need to store, the kernel needs to store the values of these registers before the kernel itself starts modifying these registers. Then the kernel will select, by invoking the scheduler, it will select the process to execute next. Let's call that process that will be executing next process number 1. So process number 1, now the system, before giving control, before giving the CPU to process number 1, it's going to reload the state. So it's going to set the values of the CPU registers to the values that were stored in the process control block that belongs to process number 1. Now, where would the process control block physically be? So physically, where would the process control block be?
Storage?
Hmm?
Would have been storage?
What kind of storage? Yeah.
Hard
Well,
disk?
so the kernel, the cache is hardware controlled, so the kernel would just have to push it to memory in hopes that it goes to the cache?
Yeah, well, it will be in memory, whether it's cached or not. Yeah, that's under the hardware control. Yes, you are right. So it will be in memory, but it will be specifically in the kernel address space. Right? So the process control block is a kernel data structure that will be in the kernel address space in memory. Okay. So then we will reload the state just to so that you are clear on the kind of where the information will be flowing or moving. So in this case, when I save the state of process number 0, the information or the data is getting moved from CPU to memory. The values of the registers are saved to the values that are on the CPU are stored in memory. Here, we are loading into the CPU. We are loading from memory into the CPU the values of the registers. Okay? Then process number 1 is executing, and at some point, process number 1 will lose possession of the CPU for one of the different reasons that we have explained, either because it requests I/O or because it gets interrupted by the timed interrupt. And in that case, the system will do the same. It will save the state of process number 1 into the process control block. and then the kernel will do its work, and then it will select a process to get the CPU next, and assuming that that process, which will get the CPU next, happened to be process number 0, the system now will have to reload the state of the process number 0. So now the transfer here, data goes from memory into CPU, right? From the process control block, which is in memory, into the CPU. Okay, so it looks like this. This is memory, and the kernel will have its own address space. So this is the kernel address space, and in the kernel address space there will be the kernel code and the kernel data structures, the kernel data. And among these data, there will be, process control block for process 0, process control block for process 1, process control block for process 2, and so forth. So among many, many other data structures that the kernel will keep in memory. Now I have a couple of questions to make sure that everything is clear. Now, while during this time here, the kernel will be doing something. Now, what the kernel does here, what do you think the kernel will be doing? And we mentioned in previous lectures, we talked about the things that the kernel will be doing in this save and this reload. So, give me a couple of important things that the kernel.
Scheduling.
What's that?
Scheduling.
Yeah, it will be definitely invoking the scheduler, because in order to decide, which process gets the CPU, it must invoke the scheduler. So one of the things that will take place here is scheduling. Besides scheduling,
Interrupt.
yeah,
You think that the kernel bit, the process manager bit or whatever it's called,
okay, it's the what is it called, by the way? Yeah, the mode bit.
from 1 to 0?
Yeah, the mode bit will get flipped from user mode to kernel mode. Well, here in the beginning, the kernel will change it from when the kernel first gets possession of the CPU, it will change it to kernel mode. Then, when the kernel gives the CPU to another process, it will change it to user mode. And it's extremely important to do this. If the kernel doesn't change it to user mode, then it will be giving the user the kernel privileges. So this is one important thing. Other things that the kernel will be doing here, trying to figure out what these dots stand for. Yeah. What else? So if you were writing the kernel, what would you do? Here. Now, well, changing the states of the processes, right? Changing the states of the different processes. Now, what will the state of P0 change to here in this case? The change of, now here, what was the state of P0? Running, yeah.
Running, yeah.
Yeah, so P0 was running. Now, the kernel now will change its state to what?
Ready.
Well, ready, it's not necessarily ready. It depends on,
If it was, if it called for like an I/O event, or if it had a problem and it has to terminate.
so if it was an I/O event, what would the state change to?
Wait,
Wait, yeah. So if the cause of this interrupt was a system call requesting I/O, then the system is going to change the state of P0 to waiting, because it will be waiting for that I/O request or waiting for that system service in general, whether it's I/O or something else. So it's going to change the state of P0 to waiting. But if it's a timed interrupt, if the process got interrupted by the kernel, then the state of P0 during this time will be what?
Ready.
Ready. It will be ready. It's not waiting for anything. The system just interrupted it so that it can give the CPU to another process. Okay. And this time is called idle, even though idle is not a it's not the best word to use, I think, in this case, because something useful is happening, but from user point of view, the CPU now is in possession of the kernel, the system. And this is something that we would like to minimize. In a good system, if the system is running efficiently, then 99.9% of the time, the CPU should be in possession of a user process. The kernel should do its job with minimal CPU time. So this is idle in the sense that the kernel is running on the CPU. None of the user processes are running on the CPU during this time. These are important concepts, and like I said, everything in this class will be built on these concepts.